So in this class, we will get started with mechanical properties of solids. So first, let us see the introduction. So in the chapter system of particles, we have studied about the rotation of the bodies. And then we realized that the motion of a body depends on how mass is distributed within the body, and we restricted ourselves to simpler situations of rigid bodies. And a rigid body generally means a hard, solid object having a definite shape and size. But in reality, bodies can be stretched, bodies can be compressed, and bodies can be bent. So even the appreciably rigid steel bar can be deformed when a sufficiently large external force is applied on it. This means that solid bodies are not perfectly rigid. So what is the property of a solid? It has definite shape and size. So in order to change for the shape or size of a body, or you want to deform the size and shape of the body, some force is required. If you stretch a helical spring by gently pulling its ends, then the length of the spring increases slightly. When you leave the ends of the spring, it regains the original size and shape. So, the property of a body by virtue of which it tends to regain its original size and shape when the applied force is removed is known as elasticity, and the deformation caused is known as elastic deformation. So, first let us write down the definition of elasticity. So, let's see what is elasticity. So, the property of a body by virtue of which it tends to regain its original size and shape when the applied force is removed is known as elasticity. And the deformation caused is known as elastic deformation. So, however, if you apply force to a lump of dough or clay, they have no gross tendency to regain their previous shape, and they get permanently deformed. So, such substances are called as plastic, and this property is called as plasticity. So, which cannot regain its original shape and size by itself, that is called as plastic, and the property is called as plasticity. So, dough and clay are close to ideal plastics. So, the elastic behavior of materials plays an important role in engineering design. For example, while designing a building, knowledge of elastic properties of materials like steel, concrete, etc., is essential. The same is true in the design of bridges, automobiles, ropeways, etc. So one could also ask, can we design an aeroplane which is very light but sufficiently strong? Can we design an artificial limb which is lighter but stronger? Why does a railway track have a particular shape like eye? And why is glass brittle while brass is not? So, answers to such questions begin with the study of how relatively simple kinds of loads or forces act to deform different solid bodies. So, in this chapter, we shall study the elastic behavior and mechanical properties of solids, which answer many such questions. Now let us move on to elastic behavior of solids. So we know that in a solid, each atom or molecule is surrounded by neighboring atoms or molecules. So these are bonded together by intermolecular or interatomic forces, and they stay in a stable equilibrium position. So when a solid is deformed, the atoms or molecules are displaced from their equilibrium positions, causing a change in their interatomic or intermolecular distances. So, when the deforming force is removed, then the interatomic forces tend to drive them back to their original positions. Thus, the body regains its original shape and size. So the restoring mechanism can be visualized by taking a model of spring ball system as I have shared you. So here the balls represent atoms. Can you see the black circles? Those represent the atoms, and the springs which you can see, those represent interatomic forces. So if you try to displace any ball from its equilibrium position, then the spring system tries to restore the ball back to its original position. Thus, elastic behavior of solids can be explained in terms of microscopic nature of the solid. So, Robert Hooke, he was an English physicist. He performed experiments on springs and found that elongation. What do you mean by elongation? It is the change in the length. So, he found that the elongation produced in a body is proportional to the applied force or load. So in 1676, he presented his law of elasticity, now which is popularly called as Hooke's law. So we shall study about it in the next section. Now this law, like Boyle's law, is one of the earliest quantitative relationships in science, and it is very important to know the behavior of the materials under various kinds of load from the context of engineering design. So after understanding the elastic behavior of solids, let us move on to stress and strain. So when forces are applied on a body in such a manner that body is still in static equilibrium, then it is deformed to a small or large extent depending upon the nature of the material of the body and the magnitude of the deforming force. So the deformation may not be noticeable visually in many materials, but it is there. So when a body is subjected to a deforming force, a restoring force is equal in magnitude but opposite in direction to the applied force. So how can you define stress? So stress is the restoring force per unit area. If suppose F is the force applied and A is the area of cross section of the body, then magnitude of stress is F by A, and SI unit of stress is Newton per meter square or Pascal, and its dimensional formula is M L power minus 1 T power minus 2. So there are three ways in which a solid may change its dimensions when an external force acts on it. Now you can see I have drawn 4 figures over here. So there are 3 ways in which a solid may change its dimensions when an external force acts on it. So you can see by this figure, in the first figure, that is A figure, a cylinder is stretched by 2 equal forces applied normal to its cross-sectional area, and the restoring force per unit area in this case is called tensile strength. Tensile stress. So the restoring force is called tensile stress here. And if the cylinder is compressed under the action of applied forces, then the restoring force per unit area is known as compressive stress. When it is compressing, it is compressive stress, and when it is expanding, it is tensile stress. So tensile or compressive stress can also be termed as longitudinal stress. So in both the cases, there is a change in the length of the cylinder, whether you expand it, whether you stretch it, or you compress it. In both the cases, there is a change in the length. So the change in the length, that is delta L, to the original length L of the body, is known as longitudinal strain. So the change in length is, that is delta L, is called longitudinal strain. So how can you write longitudinal strain? So longitudinal strain is equal to delta L by L. So however, if 2 equal and opposite deforming forces are applied parallel to the cross-sectional area of the cylinder, as you can see in the second figure, that is B figure, then there is relative displacement between the opposite faces of the cylinder. And the restoring force per unit area developed due to the applied tangential force is known as tangential stress or shearing stress. So in the B bit, it is tangential stress or shearing stress. And in the A bit, it is tensile stress or compressive stress. Now, as a result of applied tangential force, there is a relative displacement delta x. You can see in the second figure how I mark delta x between opposite faces of the cylinder as shown in the second figure. So, the strain so produced is called shearing strain. And how can you define shearing strain? I am writing over here shearing strain formula. Shearing strain is delta x by L because it is tangential stress. So it is tan theta. And it is defined as ratio of relative displacement of the faces delta x to the length of the cylinder L. And here it is given by tan theta, where theta is the angular displacement of the cylinder from the vertical, that is original position of the cylinder. So usually theta is very small. So tan theta is nearly equal to angle theta. So if theta is equal to 10 degrees for an example, then there is only 1% difference between theta and tan theta. And it can also be visualized when a book is pressed with the hand. As you can see the third figure, C figure. A book is pressed with a hand and pushed horizontally. So then shearing strain takes place. So over here, shearing strain takes place, which is equal to tan theta and which is equal to theta. And in the last figure, you can see a solid body placed in the fluid under high pressure is compressed uniformly on all sides. So the force applied by the fluid acts in perpendicular direction at each point of the force and the body is said to be under hydraulic compression. In the fourth bit, it is hydraulic compression. So this leads to decrease in its volume without any change of its geometrical shape. So the body develops internal restoring forces that are equal and opposite to the forces applied by the fluid. That is, the body restores the original shape and size when taken out from the fluid. So the internal restoring force per unit area in this case is called hydraulic stress, and its magnitude is equal to the hydraulic pressure, that is applied force per unit area. And the strain which is produced by hydraulic pressure is called volume strain, and it is defined as the ratio of change in volume to the original volume. So let me write over here what is volume strain. Volume strain is change in volume, that is delta V, by original volume V. So since strain is a ratio of change in dimension to the original dimension, so because numerator and denominator has same units, so the units get cancelled, and finally it has no units and it doesn't have any dimensional formula. Now let us understand the most important topic, that is Hooke's law. What is Hooke's law? So stress and strain have different forms in the situations, how we have depicted in the last picture, that is in the 4 cases. So for small deformations, the stress and strain are proportional to each other. That is Hooke's law. So what is Hooke's law? Stress is directly proportional to strain. So if I want to remove the proportionality symbol, I need to place a proportionality constant. So we can say stress is equal to K into strain, where K is proportionality constant and this K is known as modulus of elasticity. So Hooke's law is an empirical law and it is found to be valid for most materials. However, there are some materials which do not exhibit this linear relationship. Now, after understanding Hooke's law, let us see what is stress strain curve. So the relation between the stress and the strain for a given material under tensile stress can be found experimentally. So in a standard test of tensile properties, a test cylinder or a wire is stretched by an applied force. So the fractional change in length, that is strain, and the applied force needed to cause the strain are recorded, and the applied force is gradually increased in steps and the change in length is noted. A graph is plotted between the stress, which is equal in magnitude to the applied force per unit area, and the strain produced. So a typical graph is seen. So like if you see, if we take strain on x-axis and stress on y-axis, and if suppose this is less than 1%, so you get like this. This is sigma y, and this is sigma u, and this is fracture point, and this is permanent set. So if we take, let's say 30% over here. So you can see a typical graph is drawn. So analogous draws for compression and shear stress may also be obtained. So the stress strain curves vary from material to material. These curves help us to understand how a given material deforms with increasing loads. So from the graph, we can see that in the region from O to A, the curve is linear. Now in this region, Hooke's law is obeyed and the body regains its original dimensions when the applied force is removed. So, in this region, the solid behaves as an elastic body. Now, if you look at the graph, in the region from A to B, stress and strain are not proportional. Nevertheless, the body will return to its original dimension when the load is removed. And the point B is called as yield point. This B is called as yield point, also called as elastic limit, and the corresponding stress is known as yield strength, that is sigma y of the material. And if the load is increased further, then the stress developed exceeds the yield strength and strain increases rapidly even for a small change in the stress. So the portion of the curve between B and D shows that. So when the load is removed, say at some point C between B and D, then the body does not regain its original dimension. So in this case, even when the stress is zero, the strain is not zero. So the material is said to have permanent set. And the deformation is said to be plastic deformation. And the point D on the graph is ultimate tensile strength of the material. So beyond this point, additional strain is produced even by a reducing applied force and fracture occurs at point E. And if the ultimate strength and fracture points D and E are close, then the material is said to be brittle. If they are far apart, the material is said to be ductile. So as we have stated earlier, the stress strain behavior varies from material to material. For example, rubber can be pulled to several times its original strength and still it returns back to its original shape. Now you can see I have drawn a graph. This graph shows stress strain curve for the elastic tissue of aorta, which is present in the heart. And you note that although elastic region is very large, the material does not obey Hooke's law over most of the region. Secondly, there is no well-defined plastic region. Substances like tissues of aorta, rubber, etc., which can be stretched to cause large strain, are called elastomers. What are they called? Elastomers. So which can be stretched to cause large strains. Those are called elastomers. Now let us see what is elastic moduli. So the proportional region within the elastic limit of the stress strain curve, which you can see in this curve from O to A, is of great importance for structural and manufacturing engineering designs. So the ratio of stress and strain is called modulus of elasticity, and that is found to be the characteristic of the material. So what is modulus of elasticity? Stress by strain. Now let us move on to the most important topic, that is Young's modulus. What is Young's modulus? So experimental observations show that for a given material, the magnitude of the strain produced is same whether the stress is tensile or it is compressive. So the ratio of tensile stress to the longitudinal stress is called Young's modulus. So what is Young's modulus? Young's modulus is denoted by Y, and that is tensile stress, which is denoted by sigma, by longitudinal strain, which is denoted by epsilon. So we can say Y is equal to sigma by epsilon, where sigma is tensile strength and epsilon is longitudinal strain. So we know that Y is equal to F by A into delta L by L. So that is F into L by A into delta L. So since strain is a dimensionless quantity, the unit of Young's modulus is same as that of stress, that is Newton per meter square or Pascal. So if you can see this table, I have shown you Young's modulus, elastic limit and tensile strengths of some materials. So from the data which is given in this table, it is noticed that for metals, Young's moduli are large. Therefore, these materials require a large force to produce small change in length. And to increase the length of a thin wire of 0.1 centimeter square cross sectional area by 0.1%, a force of 2000 Newton is required. So the force required to produce the same strain in aluminium, brass and copper wires having the same cross-sectional area are 690 Newton, 900 Newton and 1100 Newton respectively. So it means that steel is more elastic than copper, brass and aluminium. And it is for this reason that steel is preferred in heavy duty machines and in structural designs. So wood, bone, concrete and glass, they rather have small Young's modulus.